Hello, 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 hello. Welcome to the Shield Tracker Programming 101. So this is more of a quick recording test than anything else. So I'm hoping to create like a more polished tutorial at some point. But anyways, just want to give like the fundamental introduction. So the idea behind this programming language is that you can basically extend the tracker with your own functionality. So you have these commands here in the pattern, and the idea is that you can just write your own ones using this programming language. And the way you do that is you use call program, and you create a program, and now whenever the step would be played, it will call this program and execute it. In this program, you can do basically everything that you can do with these commands, as you can call them from the programming language. All right, so this is the program editor, and like the most important columns are these two. So we have the opcodes here, and we have some memory addresses or addresses that we can read from. And then on the right, so these are only display columns, and they show you the values that are currently stored in memory. So we have three different kinds of memory. So we have local memory, global memory, and a stack. The local memory is like a memory that is local to each track. So each of the 16 tracks has its own local memory. And then we have the global memory that is shared across all of the tracks. And so we can use this memory region to communicate between the tracks. So one track can write a value in there and another one can read it. All right, so let's just start by executing this very simple program. So I just made this pattern one step long, just so that that we repeatedly call this once I start the sequencer, which I'll just do now. And let's just write a value into memory to see what is happening. So the way we do that is we first have to load a value into one of the CPU registers. So they are basically like temporary variables that you use for computation and stuff like that. So the main register is this accum register that we can use to do math functions with. And then we can just load a value into this register. And once we have loaded it, we can also store the value into, for example, our memory. So we can use the local memory here, local memory address 0. And now you can see in this L column that this value is showing up there. So like whenever the step is executed. We can also do computation on these values. So if we use this arithmetic instruction here, we can, for example, like add the value, let's say 1 to it, and now we can see it first gets loaded with this value 8, and then it adds the value 1 and stores it into memory, and we can see on the right we get 9. Nice. Okay. So that's on a very fundamental level how it's supposed to be used. And let's create like a very simple example. So we have this chiptune synth here, and I made the pattern 16 steps, and if I run it, we can just hear this short blip. Another way I can do this is by using this emit node at column command. So we tell it which node column. We only have one column, so we use index 0. If we hover the cursor over it, we can also see, no, we cannot see the column index. Okay, but this is the first node column, so index 0, and then we can just place a node value there. And now I can remove this one here, and we will still hear the same blip. All right. And let's just do the same thing now, but using this programming language instead. So we create a new program here. And the way we execute these commands is using this xop execute pattern opcode. And we then use, again, emit node at column. Now, if we go back to the pattern here, you can see that we have these two arguments that are passed to this node command. And we need to do the same in the programming language here. And the way that we do that is using the index registers. So if you remember, like this load instructions, so it gets a register as an argument here. And so we can use this index x, which becomes the first argument of this node command here. So we want to fill this with the value 0. And then the index y command, this would be where we specify the node value. We can do that using this immediate node value. And let's play maybe F3 here. And now we should get another bleep here. Nice. All right, so this is maybe not the most exciting pattern, but for example, instead of like hard coding this node value here, we could use something based on the modulators. Just as a brief reminder, so the modulators, they are like, there's 16 modulators and you can program the speed and the waveform of it. So they are basically LFOs that you can freely assign or use for whatever you want. And if you start the sequencer on the right, these lines that are moving, so these are the outputs of the different modulators. To access them in the programming language, we can use as a memory address, we use special, and then we use modulate. So this is the modulator. And since there are 16 of them, we also need to specify which one we want to access. All right, so let's first load this into the accumulation register, and then we also need to specify using index x which of the modulators we actually want to use. So let's just use modulator 0. And now we would have the value of the modulator in our accum register. And instead of using the node value here, we could then use the accum register. And now when we run this pattern, instead of outputting a fixed node, we will output whatever is just the value of the modulator. So let's see what happens. All right, we're going out of range here a little bit. So what we can do here is just make these values a little bit smaller. So for example, divide them by a value. That's excuse me. And now let's say we want to have this happen on each step. What we can just do is we use a table, and then we can just call the program number 4 here, make this table 1 step long. And now on each step, we would call this program here. So we can remove this one, remove this one, remove this one, and this one too. And get the modulator mapped to the note pitch, and we can set the waveform of the modulator, for example, to ramp down. We could make it faster. So this is in steps. We can make this a little bit faster here. Alright, yeah, what else can we do? Let's say we want to offset this, so we can just add a bass note to it. So now it would all start at C2. Yeah, so this is kind of like the most basic way to use the programs, I guess.